Thanks. It's a pleasure to come and talk to you. So I'll be talking about ways of learning about the first stars and galaxies using the 21 centimeter line of hydrogen, especially in the context of how next generation radio telescopes might be able to make those observations. And I'll touch upon a little bit of atomic physics along the way, but this will be a fairly broad overview. And I apologize at the beginning that I have a lousy cold, so this will be punctuated with coughs and sniffles. Just to set things in context, I mean, modern cosmology has done this very good job of giving us a broad brush history of the universe, from observations of the epoch when hydrogen recombines to form the cosmic microwave background. And in that we see the small density fluctuations that grow over cosmic time into the kind of galaxies that we see in the Hubble ultra-deep field. But this period of the first billion years is really observationally very poorly constrained at the moment. And you can divide that into three patches: the cosmic dark ages before the first galaxies form, when the cosmic dawn, where the light from those first galaxies begins to heat the gas between the galaxies, the hydrogen and the helium. And then reionization, when ionizing radiation from those galaxies ionizes bubbles that grow over time and percolate, leading to a phase transition from a largely neutral universe to a largely ionized universe. And as I say, this is really at the limits of current observations. And so in this talk, I'll begin just by recapping some of the things that we think we know about reionization, and then talk about ways of learning more from the 21 centimeter line, specifically from the 21 centimeter global signal and from 21 centimeter fluctuations. And if you've ever been to a talk on reionization, you've probably seen this cartoon of the cosmic history before. And I really like it because it always reminds me of this cartoon of a New Yorker's view of America. It's very detailed down here. It's very simple up here. And if you've ever been to California, you know there's a lot going on out there. And so I think that bodes well that at the moment we have very simple questions about the early universe, but as we learn more, we'll fill in the gaps and have more sophisticated questions. And it's difficult to make predictions, but the next 10 years or so is going to be a really good period for this field because of lots of new instruments that are being built. So let me begin just by saying a little about what we think we know at the moment. And one of the first probes of this epoch of reionization comes from Hubble, from the Hubble ultra-deep field, and this beautiful picture of many, many galaxies. Now, some fraction of those galaxies are at redshifts above 6 or so, and you can identify the redshift by looking at an intrinsic break in the spectrum of those galaxies and seeing how it redshifts between different color filters, and looking for the break between filters where you see it and filters where you don't. So if you do use that dropout technique, then you can count the number of galaxies in the Hubble ultra-deep field and work out the number as a function of their brightness. And if you can do that, then that tells you something about the properties of the galaxies driving reionization and enables you to count the ionizing flux to some extent. But there are caveats that the ionizing radiation lies at shorter wavelengths than the wavelengths that you actually observe. And you tend to only see the brightest sources, not the fainter ones, which can contribute significantly to the ionization budget. Another problem is that we have this picture of galaxies that ionize the universe. So these are two slices from a simulation. The dots here are galaxies, and this is about 130 megaparsecs on a side. That leads to this ionization field. The white regions here are the ionized regions, and black is neutral. And if you look at the size of the Hubble ultra-deep field to scale, it's tiny compared to the characteristic sizes of these ionized bubbles. So you're learning about galaxies, but in a relatively small patch of sky. And you'd like to have some broad-scale information to add to that. So you can go to other techniques, and one of the classic ones is the Lymanalpha Forest. So here you look for absorption in the spectrum of a high redshift quasar. And that probes a one-dimensional skewer through the intergalactic medium. You see this forest of lines, which are appearing where that light is going through dense, neutral clumps of hydrogen. And if you make assumptions that the gas is in photoionization equilibrium, then the amplitude of this level here tells you something about the transmittance of Lyman alpha photons, and that connects to the ionizing background. If the ionizing background is higher, there'll be less neutral hydrogen. So more transmittance of Lymanalpha photons, so the flux that you see will be larger. So looking at the statistics of these lines can tell you about the ionizing background and also about the temperature of the gas, but only at redshifts below 6 or so, because once you start going to higher redshifts, the amount of neutral hydrogen that's present is enough that you don't see a forest of lines, you just see what's known as a Peterson Trough. And this is a consequence that the optical depth for Lyman-alpha photons in a fully neutral IgM is about 10 to the 4, 10 to the 5. So you only need about 1 part in 10 to the 4 neutral hydrogen for all of the flux to disappear. So the fact that you don't see this at redshifts below 6 or so is telling you that the universe is mostly ionized. But it's really anyone's guess what's going on in the universe above that. And the other key piece of information that we have comes from observations of the CMB. So when the universe goes from being ionized to neutral at recombination, those CMB photons are able to free stream to the present day. But some small fraction, about 10% or so, 8.7%, scatter off the ionized plasma after reionization. And you can measure that from the large angular power spectrum of the CMB. So that gives you one number that constrains the integrated ionization history. But many different models can be fit through that. And one way of interpreting that is if you assume that the universe was instantaneously ionized, then the WMAP optical depth measurement constrains the redshift of reionization to be somewhere around 10 or so. But what we really like to do is to put everything together and learn about reionization. So this is just a cartoon of that, with the black being ionized now. So quasars give you these skewers at late times. The observations of the Hubble Ultra Deep Field tells you something about galaxies going right back into the middle of reionization, but on relatively small patches. And the CMB gives you some integrated constraint. And between that, there are lots of questions that are left unanswered about when exactly reionization takes place. So one approach is to try to improve these existing techniques and combine them more consistently. And another is to go for new observational techniques, which is really what I want to talk about in the context of the 21 centimeter line. And so there's a couple of basic questions that one might like to address. One is, if you ask, what's the neutral fraction of hydrogen? What's the temperature of hydrogen in the bulk of the universe as a function of redshift? Then I can draw theoretical curves for how those quantities evolve. But if I look at the observations that we have, they only constrain a small patch of that. So the CMB is telling you something about when hydrogen recombined for the first time at a redshift of 1,000 and the gas temperature then. Quasars tell you the universe was ionized below a redshift of 6 or so and tell you that it was hot. But this intervening space is essentially unknown at the moment. And that's, in some sense, telling us that we don't know very much about the properties of galaxies in that intervening period. And so one of the hopes of the 21 centimeter line is that you can get observational constraints on a period from when the gas thermally decoupled from the CMB through to reionization at redshift of 6 or so. So you can ask questions about the broad global evolution of the universe. You can also go the other side. So we have this picture of hierarchical structure formation, where the density field grows over time from being small fluctuations and linear to producing halos that host the galaxies. Those galaxies lead to an ionization field. And as I said, if you look at the sort of galaxy surveys that we have that are deep enough at the moment, they're very small compared to this. So you'd like some large-scale observation that measured the structure of these bubbles, and the 21 centimeter can play that role. So you have those broad brush features and then the details of structure. And in this talk, I want to talk about two techniques for using the 21 centimeter line that can address those kind of questions. So those two approaches have analogies to CMB experiments. So you're familiar with Kobe-Firaz that measured the CMB blackbody. So that was an absolute temperature measurement as a function of frequency. And you can do the same with single radio dipole experiments to measure a spectral distortion in the tail of the CMB. The alternative is, if you want to measure maps of the reionization field, then you can use interferometers such as the MWA, which Harvard and MIT and places are involved in. And that's sort of the analogy of WMAP, where you're looking at fluctuations. And so I'll discuss each of these two techniques in turn. But first, just to remind you of some of the basic physics of the 21 centimeter line and how it leads to an observable signal. So the 21 centimeter line comes from the hyperfine splitting of the hydrogen ground state. So the spin of the proton and the electron can be anti-aligned or aligned. And there's an energy separation that leads to a transition with a wavelength of 21 centimeters or a frequency of 1.4 gigahertz. Point of notation is that it's customary to describe the relative occupation number of these two levels by an excitation temperature or spin temperature just given by this Boltzmann-like factor. And some numbers to hold in your head are that if I have gas at a redshift of 6, that will produce a 21 centimeter signal that redshifts to about 200 megahertz today. Gas at redshift of 13 to 100 megahertz, and from a redshift of 20 to 70 megahertz. And these correspond to times during the first billion years after the Big Bang, going back to about 150 million years. So you're really starting to get back to the first generations of galaxies with these techniques. So putting that in the kind of cosmological context, the idea is that you can use the CMB as a backlight. So then neutral gas along the line of sight will imprint some feature at the rest frame frequency that redshifts to frequencies of order 100 megahertz. So if you pick your favorite FM radio station, that's probably blocking some useful redshift. So radio astronomers typically measure the intensity of the signal in terms of a brightness temperature. It's small, it's measured in tens of millikelvin, and it depends upon things like the hydrogen neutral fraction, the baryon density, and importantly this factor in brackets here, which is the difference between the spin and the CMB temperature. If that's positive, you get an emission signal, and if it's negative, you get an absorption signal. And there's also contributions from a peculiar velocity. So the evolution of this spin temperature drives a lot of the evolution in the total signal. So it's important to know that it gets set by three coupling mechanisms. You can absorb photons from the tail of the CMB blackbody, and that equilibrates the spin and the CMB temperature. So this factor goes to 0, and your signal dies away. Or collisions between hydrogen atoms or between hydrogen and electrons can couple the spin and the gas temperatures. And also the Wutheisen field effect, which is resonant scattering of Lymanalpha photons, can couple the spin and the gas temperatures. So just to say a few quick words in passing about those. So collisional coupling tends to be important when the gas density is high. So that's in the very early universe, or possibly in the later universe, but in collapsed structures. And the cross-section for causing that spin flip has this strong energy dependence, so it drops off quite rapidly at lower energies. That leads to a strong temperature dependence. So this is plotting essentially the rate average cross-section as a function of temperature. So below about 100 Kelvin, that drops off abruptly for scatterings between hydrogen and hydrogen atoms. The cross-section for scattering between electrons and hydrogen atoms is larger, but the fraction of electrons present is usually many orders of magnitude less. So it's this scattering rate between hydrogen and hydrogen atoms that dominate. So the other coupling mechanism is the Wutheisen field effect. The basic idea is fairly straightforward. If I'm sitting in the ground state of the hydrogen atom, I can absorb a Lyman-alpha photon and get excited into one of the 2p levels. Then I can de-excite, but to the other of the two hyperfine levels. And so I've induced a spin flip by absorption and re-emission of a Lyman-alpha photon. And there's a couple of channels by which one can do that. So this couples the spin temperature to the gas temperature via subtle atomic physics, which unfortunately I won't go into today. People like George Rubicki have done a lot of work on that here. But the net effect is to couple the spin temperature to the gas temperature. So then the question becomes, what is the gas temperature? And that's going to be set by whatever the thermal history is, which we think is dominated by X-ray heating in the early universe. So these are X-rays, can be X-ray binaries in star-forming galaxies. There can be absorption onto black holes, or inverse Compton scattering of CMB photons off the energetic electrons in supernova remnants. So at the moment, there are only weak constraints on the kind of X-ray backgrounds that people like Mark have looked into. And so we're really in the dark, and you have to make a best guess by extrapolating local properties of X-ray sources to high redshifts. And you end up with about 1 keV for every baryon that this goes into stars. And just to, one of the reasons why X-ray heating is so important is because X-rays at keV energies have very long mean free paths. So if I take a 2 keV X-ray at a redshift of about 15, its mean free path is of order the size of the universe. So these X-rays can travel very long distances, heating the gas far away from the sources. So an X-ray will photoionize a hydrogen atom, producing an energetic photoelectron. Then that electron deposits its energy by scattering off hydrogen and helium atoms, deposits it as further ionizations, as heating, and you can also end up producing Lymanalpha photons. So you can excite a hydrogen atom to, say, a 4p state, and then as there's an atomic cascade after that, Lymanalpha photons can be produced. So if you put that all together, then you begin to be able to make predictions for what the 21 centimeter brightness temperature signal will look like. So that's shown in this bottom panel. So I'm plotting the brightness, the measure of the flux of the signal, as a function of frequency. So that means that early times are at the left-hand side, late times closer to us are down the right-hand side, and redshift goes from right to left. So let me talk you through the different aspects of this signal, as they correspond to different bits of astrophysics. So just slightly to the left of this, at a redshift of about 200 or so, the gas temperature thermally decouples from the CMB as the universe is expanding. After that, the gas is able to cool adiabatically, and so it becomes cold. Collisions are sufficient to couple the spin and the gas temperatures, and that leads to this absorption feature here. So the turnover at a redshift of about 80 is because as the universe is expanding, the rate of collisions decreases, and so eventually that collisional coupling doesn't become very effective, and the spin temperature relaxes back to the CMB temperature, and the signal dies away. Now, once the first galaxies switch on, they produce a background of Lyman-alpha photons, and the Wutheisen field coupling comes into play, and that leads to this second, potentially deeper absorption trough. And this time the turnover here is because at this point things like X-ray sources switch on, and you heat the gas from absorption into emission. And then at a later stage, as stars switch on and begin ionizing the universe, the signal dies away just because there's no more hydrogen, neutral hydrogen left over, and eventually you get to almost zero signal. So this is, yes? Yeah, oh yeah. Yes. So, yeah. So you can imagine a situation where, for some reason, you move the point at which stars switch on to the right-hand side, so that you have a long period where there's zero signal, and then you get a trough or something like that. And so I think it would be straightforward to come up with physics that led to stars not switching on until relatively late. Pushing star formation earlier, that's more challenging, I think. Just because when you get to sort of a redshift of 80 or so, you're still very much in a linear regime. So there aren't many regions where dense regions have collapsed and could possibly form stars. It's not impossible, but I think that's very unlikely. But I think that brings up very much the next point that I wanted to make, that what I just described is kind of a convenient story that we tell. But given high levels of ignorance about the early universe, the picture could be very different. And one could imagine if heating doesn't switch on, then this signal can become much deeper and only turn around once you start to ionize the universe. If Lyman alpha photons didn't propagate very well, then you might have very little signal to observe. Or if heating was very effective, then you might heat up to this higher red saturated curves. So if you could observe this, then you could learn the answers to some of these questions. And so I'd like to talk a little bit about how one might observe that. And because this is an all-sky signal, you don't need big interferometers to do that. You could potentially do it with just single dipole experiments. So you're not resolving structure, you're looking at a mean signal. And so the idea then is to flick between looking at the sky and looking at some calibration source so that you can make an absolute temperature measurement as a function of frequency. Now the problem with that, and I should mention that this is the EDGES experiment being run by Judd Bowman, who will be talking at the conference. It sits out in the Australian outback. So the problem with these experiments is when you look at the sky, the first thing you see isn't the 21 centimeter signal, it's the galaxy. So the galaxy is producing a lot of radio emission from synchrotron electrons spiraling in magnetic fields. And if you look at that as a function of frequency, so as a function of frequency is the amplitude of the foregrounds, they're very large. They can be thousands of Kelvin, but they're very smooth, whereas your 21 centimeter signal is very small, tens of millikelvin, but it has this this frequency structure. So the hope is that because there's this difference, the foregrounds are smooth and you have structure in your signal, that you might be able to separate the two out by fitting out the foregrounds. And so an example of that is if you were to look at the end of reionization, so then the 21 centimeter signal, plotted here as a function of frequency, just looks like a step. So you go from a fully neutral universe to a fully ionized universe, and you get that drop. And so these three curves indicate models where reionization takes a different length to complete. So this is where it happens in a redshift interval of 0.2, of 1, and of 2. And so the idea is that if reionization is very abrupt like this, then it looks quite different from the shape of the foregrounds. And so you might be able to learn about it. But as you get to more extended reionization histories, it becomes more difficult to remove the foregrounds. And just to give you a sense of the kind of data that people have, this is some data from the EDGES experiment. So you have this diffuse component that's coming from the foregrounds. It rolls over at the edges due to the instrumental response. And then you have these sharp spikes from radio transmitters. And this is for about 50 hours of data between about 100 and 200 megahertz. So probably stealing some of Judd's talk from later in the week, but they go away and they try to constrain this duration of reionization. So this plot here is interpreted as this is the frequency at which reionization took place in the model, and this is the duration of it. Durations that are more abrupt are down here, and they're excluded, so that more extended reionization histories aren't constrained. And the limit that they can set is on reionization histories that occur in less than 0.1 of a redshift interval. That's very fast. And one of the questions then is, that's the state of the art at the moment, but how can one push these things forward to learn about reionization with better instruments and longer integration times? It's a calculation that Avi and I worked on. So we use a Fisher matrix, which is a technique in cosmology for making predictions for instruments. You model the foregrounds, you model the shape of the signal, and you understand the thermal noise. And you can use that to work out the region of reionization parameter space that one might hope to constrain. So here we're modeling the 21 centimeter signal just as a tangent function. So it occurs at some redshift and it has some duration delta z. So redshift of reionization goes along the bottom here, duration here. The green and the red curves, just to guide the eye, are the constraint on that reionization parameter space from the WMAP optical depth measurement. So that says something about when reionization took place, but it says very little about the duration. And so the green is the 1 sigma allowed region, and the red is the 2 sigma allowed region. Then the yellow region is the region that's excluded by those Lymanalpha Forest measurements. if you assume that the universe is fully ionized at redshift less than 6 or so. And these wiggly curves are the region where these edges-like experiments, these single dipole experiments, might place constraints. And the different curves are for different amplitudes of the different levels of structure in the foregrounds. So if the foregrounds are very smooth, then you can constrain reionization histories with delta Z of 2 or so. If they've got more structure, you're less able to say anything. And this blue region is where we are at the moment with edges. So there's a lot of room for improvement by pushing these experiments forward. But I think the place where potentially one could learn more is by pushing to lower frequencies and trying to observe this absorption trough that I talked about. So here the position of this trough depends upon the X-ray emission and the Lyman-alpha emission, and also on the atomic physics of those processes. So if I increase the X-ray heating, then this absorption trough moves to earlier times and becomes shallower. If I increase the Lyman-alpha absorption, then it becomes deeper and occurs earlier. So I'm increasing the strength of the coupling much earlier on. And so the question is, could one measure that? And if you go after measuring that, what are the features that one should look at? So the actual details of the shape are quite uncertain because of redshift evolution in the sources and so on. But probably the key features are the existence of these turning points that describe the shape of that signal. And you have this initial turning point for this absorption trough. And that just depends upon the atomic physics of collisional coupling and physics after recombination. So in principle, we know where the position of this trough is very well. And I just plot that in this frequency against brightness temperature region. The position of this maxima here depends upon the Lyman-alpha coupling. And if I've got a lot of uncertainty in the astrophysical parameters, and if I vary them by the sort of allowed region of uncertainty, that leads to this little locus of points into where that might occur. This deep absorption minimum depends upon the heating and the coupling, and the position is very uncertain. And then you have this maximum, and again, that's very uncertain, and reionization that I talked about. So, the hope is that one could measure the positions of these turning points and learn about the signal and use that to constrain aspects of the astrophysics. And just to give a sense of how well one might be able to measure them, here's that same curve that I've been showing. And these error bars are for an edges-like experiment integrating for 1,000 hours between 40 megahertz and 120 megahertz. And just for comparison, these red and blue curves indicate the same signal, but if I increase or if I vary the X-ray or the Lyman-alpha emissivity by orders of magnitude. So you could measure those parameters of order a few or so, provided that your assumptions about all of the atomic physics that go into it are well placed. And just to say that anything you can do from the ground is better in space. And so you can think about putting radio dipoles into orbit around the moon, and then when they're on the far side of the moon, they're shielded from radio interference from the ground. And so maybe that wins you something in terms of your signal. And so this DARE was a proposal that we put in. So we'll see how that goes. But yeah, so just to summarize some of this, it's interesting that there's this global all-sky 21 centimeter signal that you don't need expensive instruments to go after. You could just use single dipole experiments, provided that you can calibrate the frequency response of those dipoles, remove the foregrounds, then you can begin to answer some of the fundamental questions about the thermal and the ionization history of the universe. And with that, have prospects for learning about the first galaxies. And so there's a lot of room for improving these instruments. And at the moment, a lot of the uncertainty comes from the astrophysics, but that's only because we believe that we understand the atomic physics that underlies it all, which may or may not be true. So, yeah. As I said, there's that global signal, but a lot of the information is contained not in that global signal, but in fluctuations. So in the latter part of the talk, I wanted to say a little about that. So if you take the brightness temperature, you can decompose that into a number of different terms, coming from the spatial variation in the density, the neutral fraction, gas temperature, Lyman alpha flux. And each of these are basically telling you how much neutral hydrogen there is at a place and what the spin temperature is at a place. And if you could measure these different terms, then you could learn about different aspects of cosmology and astrophysics. So the immediate question is, if all of these terms are varying at the same time, it'd be a mess and very difficult to learn about any individual term. Now, luckily for us, it seems that on the basis of the energetics of the different processes and the spectrums of the sources, that these different terms become important at different times in the cosmic evolution. So at redshift, before star formation begins, there's only density fluctuations. Then once the first stars and galaxies switch on, they produce Lyman alpha halos that surround them, where the gas and the spin temperature are coupled, and you get a strong absorption signal. And you see the contrast between that absorption signal and regions where there's no signal. Then as there's more star formation, you get Lyman alpha photons everywhere. Everywhere the spin and the gas temperature are coupled, and you begin to pick up temperature fluctuations. And then finally, once the gas has been well heated, you pick up differences between ionized and neutral regions. And there's a little signal left over at the end from dense clumps of neutral hydrogen after reionization, but I won't talk about that here. So you'd like to convert this cartoon into a more detailed calculation. And that's been something where a lot of progress has been made in the last 4 or 5 years or so. And so one way for simulating, so these are slices of a reionization field. One way is to do a detailed numerical calculation where you have an n-body simulation of the underlying dark matter. You paint some prescription for galaxies on top of that, and then look in detail at how the radiation from those galaxies propagates. And that allows you to make detailed calculations of the shape of these ionized bubbles. But there's also a faster technique known as a semi-numerical approach, which produces this slice on the left, which has the same kind of large-scale properties, but is much smoother, as you can see. And so the idea there is that you just take a realization of a linear density field, and you can evolve that using a Zeldovich approximation to put in some of the nonlinearities. And then it turns out that you can essentially paint the ionization field on in a simple way by filtering that density field. So you're asking you're basically counting ionizing photons and asking the question, if I look at a sphere of gas, does that region contain enough galaxies to produce one ionizing photon for every atom of hydrogen within that volume? In other words, can it self-ionize that sphere? And so the filtering process for this is to pick a point, draw a large sphere, ask, are there enough photons inside it to ionize all of the gas? If the answer is yes, then that point is ionized. If it's neutral, then you draw a smaller sphere. And you keep going until you run out of small spheres to draw, in which case it would be neutral, otherwise it's ionized. And as you can see, you get this quite good agreement. And you can do this approach very rapidly, which is useful for producing large-scale boxes. So you'd also like to do something similar for putting in not ionization, but things like the heating and the coupling. And one technique that we've worked on is essentially to propagate the radiation fields analytically through an IgM with mean properties, mean ionization fraction, and then the flux at a given point just looks like a convolution between the star formation rate, this sort of 1 over r squared effect, and an optical depth dilution. And you can evaluate that very rapidly with fast Fourier transforms. So I say this because I want to show you a movie where some of these techniques were put into place, and that will illustrate the evolution of the fluctuations in a sort of more visual way. So this is 100 megaparsecs on a side, and it starts at about redshift of 25, and steps down to the present day. So if I let it run forward, initially you get these bright blue regions, which are the Lyman alpha halos that I described around the first galaxies. If I let it run further forward, then you slowly build up this strong absorption signal everywhere as more and more Lyman alpha photons get produced and couple the gas throughout the volume. Then eventually I start to see these red regions. So these are regions where the gas has been heated from X-rays, and you have this patchwork of cold gas seen in absorption and hot gas seen in emission. As you run it further forward, eventually all of the gas becomes heated above the CMB temperature, and you're seeing an emission signal everywhere. And then if I let it run further forward, you start getting these ionized regions that are expanding and percolating. And eventually, almost all of that neutral hydrogen will have been eaten up and reionization will complete. So these are just 4 panels taken from that simulation. And I talked a little about the techniques that we used for calculating this. These are sort of 3 groups that have been developing these approximate schemes: Mario Santos, Andre Messinger, Rajat Thomas. And there's also some attempts being made to do fully numerical simulations of this, but that's very challenging because you need to keep track of your radiation at many different frequency bins and for very large boxes. So these pictures look pretty, but ultimately what one wants to do is to take those and turn them into something quantitative. And for cosmologists, that's typically something statistical, like a power spectrum. So this is correlating 2 points together, measuring the correlation function of that field, and then Fourier transforming it to get a power spectrum. And so these 2 panels here show the shape of that power spectrum when I include Lyman-alpha fluctuations, the X-ray heating fluctuations. And so on the bottom panel, I'm plotting as a function of wave number. So at the left, these are large wavelength Fourier modes on the sky. And on the right, they're small wavelength modes. And the amplitude of the power and the fluctuations. And so the kind of astrophysics information that one gets out, the green curve here is for if I just have density fluctuations. So adding in fluctuations in the Lyman-alpha field increases the amount of power. On the larger scales, that tells you about the clustering of the galaxies. And on intermediate scales, that tells you something about the frequency spectrum of the sources, the sort of wavelengths of light that they're producing. And for each of these cases, you learn similar kind of information about the sources, but here about the Lyman series photon emission, and here about X-ray sources. So one needs to be aware that the power spectrum evolves as a function of time. So I showed you that movie of how the fluctuations evolve, and similarly the power spectrum will evolve as a function of redshift. So that's a 3-dimensional bit of information. So it's hard to compress onto a 2-dimensional picture, which makes this figure a little confusing. But what I'm showing here is the redshift evolution of the power spectrum. And each of these individual curves is just for a single wave number. And I'll show you a movie on the next slide that makes this a little clearer. But what I wanted to illustrate is that the evolution of the power spectrum breaks into these different regions. So you have this region where it grows smoothly and then turns over. And so here the power spectrum is just tracking the density fluctuations. And this is modulated by the mean brightness temperature. Then you have a complicated period where it wiggles around, where the heating and coupling becomes important. And then there's another region where reionization comes into play and the power spectrum flattens off. But sort of one interesting thing is that these diagonal curves indicate the level of the foregrounds reduced by an amplitude 10 to the minus 3 through to 10 to the minus 9. And that's a sort of a measure of how hard one has to work to actually observe this signal. And the same kind of line that runs through the signal for reionization also runs through the power spectrum for these coupling and heating power spectrum bit. So that in some sense, this region up to about redshift of 30 or so is as easy or as hard to observe as the period of reionization at more like redshift 10. Whereas these dark ages, density fluctuations are much more difficult to observe. So, as I say, this is a confusing picture, so let me show you a movie that I borrowed from Andre Messinger. So in the left-hand panel here, it will show a field of the fluctuations again. And on the right-hand side, you have the power spectrum. And this movie will illustrate how this wiggles about as a function of time. So if I let it run off from a redshift of 200 or so, this looks relatively featureless and evolves, tilts a little, it rises slowly up to a redshift of 50, drops off a little, and now as first stars and galaxies form, they produce these Lymanalpha photons, and the amplitude of the signal increases dramatically. So you see it shoots up there. So now it wiggles a bit as first the coupling fluctuations and then temperature fluctuations come into play, and then dies down a little, and then as the black ionized regions form, you'll see this power spectrum flatten off. So you see there it flattens, and then finally it dies away as all of the neutral hydrogen is ionized. So let me just show that run through. And so a key thing is that this power spectrum is relatively featureless as a function of wave number, but it has this wiggling about in redshift. So if you can measure it both as a function of scale on the sky, but also track that evolution, then that gives you extra handles to learn about the astrophysics that's contributing at different times. So there are other ways that one could try and separate out the different bits of physics. One is to look for something that's called redshift space distortions. So that gas is not necessarily stationary. It can be in motion, and that affects the signal that you see. So for example, if you look at an overdense region, that looks like a cloud where the gas is flowing in towards the center. And that you make observations not in real space, but in frequency space. And so that motion of the gas translates into an apparent squashing of the signal from that cloud of gas into a more ellipse. That makes the power spectrum that you're observing depend upon the angle. So if you plot it as a function of wave number, it doesn't look spherical. It has some ellipticity to it. And in principle, that leads to a power spectrum that depends on different powers of this mu term, where mu is an angle between a Fourier mode and the line of sight. So if you can measure the power spectrum as a function of angle, you could separate it out into these different components. And these three different panels just show how that power spectrum evolves. And just the take-home message is that this Y curve, which corresponds to the full power spectrum on a single scale for each of these terms, it evolves differently as a function of redshift. And so if you could measure those different terms, that would again tell you something about when and where Lyman alpha temperature density fluctuations came into play. And sort of another technique that one could use is not just to look at the power spectrum, but to look at other statistics. So this ionization field isn't a Gaussian random field. So statistics other than the power spectrum can be important. So you might look at, for example, the one-point function. So here you're essentially making a histogram of the amplitude of your signal in different observing pixels. So early on, if you're looking at a signal that's just coming from the density field, that looks very Gaussian. But then as you start to ionize the field, you start building up pixels that have zero signal. And that leads to this spike down here. So that can be measured as a skewness of the PDF and would tell you about when reionization was going on. You can also look at three-point correlations. So those correspond to triangles, and that's a bispectrum, and that would also contain some statistical information about the sizes of ionized regions and so on. So these fluctuations are interesting at the moment because people are building instruments to measure them. So this is PAPER, which is operated out of Berkeley. It's the Murchison Wide Field Array. We're in the Australian outback, which the CFA is involved in. LOFAR in the Netherlands. This is the GMRT, a radio interferometer in India. And the idea behind these experiments is you take these individual dipoles, you collect them into tiles, and cross-correlate the signal from all of the different tiles over baselines that can be meters to hundreds of kilometers, and that gives you your radio telescope. So these Pathfinder instruments are geared for detecting these fluctuations from reionization, whereas a next generation instrument, So the square kilometre array could go after those temperature and coupling fluctuations that I described. And just to show you some aerial pictures of those experiments. You have MWA in the very dry Australian outback, very radio quiet. Then you have LOFAR in the very wet Dutch countryside, surrounded by cell phones, radio stations, and everything you care to name. Paper in South Africa. And just to sort of highlight the fact that this is a field that's very much in the transition from purely theoretical to the beginning of observations. This is the GMRT, and they actually have some upper limits on the power spectrum. So they make a map of the sky, which looks like this, and you can probably just make out some slight fluctuations in there. That's just from the foreground. So then they piecewise linearly fit out the foregrounds as a function of frequency, and that leads to this wonderful map here where there's absolutely nothing. And if you zoom in, you again get these little fluctuations. And those are mostly corresponding to instrumental residuals, but the amplitude of them enables you to place an upper limit on this plot of the 21 centimeter power spectrum as a function of wave number. And so this is the upper limit that they have begins to constrain a model where the gas just cools continually after recombination, so there's never any heating, and where there are ionized bubbles that are very large. So in some sense, it's a maximal signal, and they're just starting to get to that level of sensitivity. A more reasonable amplitude for the signal is down here, several orders of magnitude lower. So there's still plenty of room to work. And to jump from these humble beginnings to the further future, if one can understand the astrophysics in this signal, there's information about cosmology and the fluctuations of the density field. And it's perhaps humbling to realize that the volume of the observable universe that we've currently observed is limited to a thin slice at a redshift of 1,000 in the CMB and a small region in the Sloan Digital Sky Survey down here. And all of this volume is totally unobserved. So the 21 centimeter signal gives you a chance to fill in an annulus out here, perhaps. And if one could do that, then you could learn a lot about cosmology. But that's somewhat further in the future. So let me just summarize the kind of state of the 21 centimeter signal with this figure. So in the bottom panel is the global signal that I described with these two absorption features and an emission feature. It's a function of frequency. And then the top-hand panel is the corresponding fluctuations as they evolve in time from this absorption dominated by density through the spin and temperature fluctuations that I showed you, and then reionization. And there's a systematic path for observing these different aspects of the signal. So I talked a little about the EDGES experiment, a single dipole going after the end of reionization, and things like the DARE satellite, or maybe EDGES at lower frequency, could go after this absorption trough and learn about the first stars and galaxies. There are these Pathfinder interferometers which really probe this end point of the fluctuations for reionization. And then in the further future, things like SKA HERA could measure this with much higher sensitivity and also push down to lower redshifts. And there are even ideas that people around here have been kicking around for radio interferometers on the far side of the moon, with names like the Lunar Array for Radio Cosmology or the Dark Ages Lunar Interferometer. But those are looking a little futuristic at the moment. But there's this sort of systematic path for probing the different epochs of the signal and really learning about the whole history of the evolution of hydrogen and of stars and galaxies. So I'll just bring that to a close. That I think is this whole field of learning about the phase transitions of hydrogen from cold and neutral to hot and ionized is going to be very exciting over the next decade as many different instruments come online. And you'd like to learn both about the galaxies that drive that evolution and about the gas itself from things like 21 centimeter observations. And so I talked about the 21 centimeter global signal. So it's essentially a relatively simple absolute temperature measurement as a function of frequency. That if you could measure it, you'd learn about basic properties of the galaxies. But you need to be able to remove foregrounds, calibrate your instrument, There's lots of challenges ahead for that. I also talked about the fluctuations, which have a lot more information about the topology of heating and ionizing and about the sources that drive that. And so in principle, there's a wealth of information out there that if one could build the right instruments and get them to work, then you could hope to measure some of this. And so this is an exciting field at the moment because these interferometers are really starting to learn about the foregrounds, and in the next couple of years, hopefully the signal underlying that. And there are even some crude level of constraints. And there's this nice picture of how one might build out to the future. So I'll end there, and this slide just kind of summarizes what I just said. So thank you very much for your attention. There would be. So I haven't looked at that in any detail. Yeah, I mean, in principle, so the place where you would probably want to, so one place that would be great to measure that is, this trough here in the Dark Ages, because that, in principle, depends upon fairly fundamental physics. So you could separate out something like the evolution of fine structure constant from astrophysics. That's fairly hard to observe. So in here, there would be some signature from the fine structure constant, but there's a lot of astrophysics going on as well, and so it's not obvious whether the two might not be degenerate with one another. So I think you'd have to work hard, but it's at high redshift, so alpha dot is large, I guess, in some sense. Thanks.